Everyone, welcome to the fourth episode of DeepTech Studio. Today we have with us Dr. Heike Riel, who has been the brain behind Europe's most powerful quantum computer in Germany. She has also been an IBM Fellow and leads the quantum research for IBM Research in Europe. And it's been a pleasure to host her. And let's learn more about IBM's research in quantum. And there has been a talk about 1,000 qubits by 2023. Let's see what Dr. Riel has to say about it. Why has there been a growing interest in this field?
Oh, quantum is definitely at like a point of inflection, which is coming up, where a lot of dynamics in the system. So quantum is not a new topic. It has been around, the idea of quantum computing has been around since 40 years, when Richard Feynman actually about really 40 years ago came up with this idea. And in the meantime, a lot of theory work, a lot of groundwork has been done by the theorists, by the experimental physicists, by engineers to bring quantum to a point where it's getting really also interesting for true applications, where we have moved from the idea, from the concept of proving the theory also, and building now a real computer, which is actually working and which can be used, which is tested, where we are now using and building and developing applications for the industry to solve big problems. This is really the interest. We are now at or coming towards an inflection point where the industry can get true value out of using quantum computers.
Let's talk more about it actually. How do you think quantum will change the face of innovation?
I mean, this is exactly a new technology, right? It's something which we haven't had before. I compare it a bit also with the silicon industry. If you go back like in the early 70s, when the first integrated circuits with about 2,000 to 4,000 transistors have been built, and they were first used as calculators, but then people realized very early that they could be also used as more like a general processor. And then since then, of course, there has been a true innovation machine going on for many, many years, coming up with new technology, coming up with new ways of using the new technology, making the technology more complex, increasing the performance of the technology, and then being able to also create new applications. And so I see this parallelism also coming to the quantum computing. We are in the early phase still, but we have developed the technology to a point that we have real quantum computers we can now use and we can apply, and we can start thinking and working on applications. This doesn't mean yet that we already have something which is better than classical computing at that point in time, but we are on the close path to demonstrate this in the near future, that quantum computers provide additional value to classical computers and solve problems which classical computers cannot solve. And so this makes it really exciting. And this, of course, makes also a lot of new innovation possible. And of course, this has to be developed, right? We cannot now predict everything what will come, but there is this wonderful opportunity that we can now write new algorithms, develop new applications, identify what are the big problems which quantum computers may solve, which classical computers cannot solve. And so if you want, I can dive also a bit deeper into why is this the case, what is different in quantum computers compared to classical computers, and where do we see this innovation. But it's really bringing up a new technology which can do different things than classical computers can do.
Sure. So yes, I will come to that as to what are the gaps and how can quantum computer bridge that gap. But before that, I want to understand, why should the masses care? And what are these problems that we haven't found solution yet? But with the advent of quantum computers, we will have solution to these problems. Where is the research going on?
Yeah, so often it is not known that the digital computers And also the high performance computers, which are super big and which can do a lot of different things. But there are still certain problems with that also HPC, like high performance computers, cannot solve. And these are special mathematical problems, but they are very relevant actually. And I give you a few examples. One is in calculating the properties of molecules or of materials in an accurate way. Today, we are not able to do this by digital computers because the problem is inherently quantum, right? The molecule is inherently governed by the laws of quantum physics. And so classical computers have a hard time to really calculate the exact properties. They can only do approximations. And of course, over the last 100 years, as physicists and chemists, we have learned how to do certain approximations in a smart way. And for some of those molecules, we can do it already very well. But also the ones we can calculate more precisely, they are very, very tiny. And we cannot expand this because the classical computers cannot, by design, not solve these big problems. There are other application areas which are in the area of optimization. A typical example is like the traveling salesman problem. I'm not sure whether you've heard of it, but it's a problem where if you are a salesman and your task is to go to different cities in the country and visit all these cities, and you want to find the shortest path of it and the most efficient way of doing this, then this problem increases its complexity exponentially when you add more cities. So actually with 10 cities, you're already in the millions of options you can choose to find the shortest path. And this type of problems you can find in many different areas, not only in the traveling, in transport, but also in the manufacturing industry. There are different parameters you want to optimize, etc. And so these are typical problems which classical computers can only solve by doing approximations, but not in the exact way. And another problem also which is typically used is, for example, the factorization. If you have a really super big number, then finding the prime number is a big problem. And our classical computers today, they would need to go through every option seriously in series, and this would take really very, very long. But quantum computers and the specific Shor algorithm, which has been developed by Professor Shor, this actually explores all these options in parallel, and this gives kind of this speed up, which can be reached by quantum computers. And these are kind of three different options. There are more examples of where quantum computers can make a difference to classical computers. And as I mentioned before, we are still in the early stage. So right now we are not there really demonstrating this, but we have the hardware and we also have a path how we scale up the quantum computers and also scale up their performance in the future. But at a certain point, we can demonstrate that quantum computers have an advantage for some of those problems.
Sure. So, okay, when we are at the discussion of scaling up and expansion, right, you made my job easier by pointing me to the next question. So IBM's focus on quantum, by 2023, you're going to be at 1,000 qubits. And it's also planned for expansion, as you said. What exactly is this? And are you closer to reaching to the goal, or what's it going to take to reach there?
So yeah, I mean, this is this question can be answered in an hour and longer because there are many technical details also to be followed up. But let's start by just giving you a bit of a timeline. Like 5 years ago, we have demonstrated the first 5-qubit chip. And demonstrating this 5-qubit chip already shows that you have managed to build not only one, but more. They interact. You can control them in the ways like you can gate them, you can implement algorithms, and you can do simple calculations. Then from a technology point of view, we need to scale up to many qubits in the future in order to also make error correction and fault tolerance true. Right now, these are not error corrected. And so this year, however, we already want to demonstrate 127 qubits. Last year, we had demonstrated 65 qubits. And so from going from 65 to 127, we already have to implement new technology in order to be able to scale up above 100. And this will demonstrate it towards the end of this year. And then next year, we want to demonstrate 433. And then a year later, as you rightly pointed out, we want to kind of break through the 1,000 qubit barrier. And you have to imagine that, you have to develop your technology further. You have to make sure that you can interconnect all these qubits, that you also bring all these lines out through your fridge. I mean, you have to cool all that stuff. So you have to go with extra lines to these qubits. You have to miniaturize the qubits, but also the connections. And you have to better control them. You have to sometimes also, you have to also reduce the errors these qubits still have. So in all these things, we are actually working. This is the hardware technology. And then we, of course, also work on the software, on how to control this, how to pulse these things. And because all this will actually affect how the performance of these quantum computers is. Because it's not only the number of qubits. I want to point this out because that's important to understand that the performance of a quantum computer is not only the number of qubits, so the quantity, but it's all of the quality of the qubits and how they interact with each other. And then in the end, also how you run them, because you always need also kind of a classical control of the quantum computation. So how you connect with your software architecture, also the quantum computing and the classical computing. And so we work holistically on this entire stack, from the hardware to the control, to the packaging, to the entire hardware system, and also to the software, the compiler, the applications, and making it in the end actually very, very easy for the user to use quantum computers. So it's not only about the number of qubits, but it's about the quality of the circuits, the variety, which means how many circuits you can run, or what type of circuits you can run, and also the capacity. Because in the end, the user just wants to solve the mathematical problem one has in the most efficient way.
Okay. Dr. Riel, is there pressure to be ahead in the race? Because now there is Honeywell, there's Google with their new quantum AI campus. How do you deal with it? What do you think would be your competitive advantage at the end of the day?
Okay, of course, you always have competition, right? It starts in research. You are never alone in your field, because if you are, then actually sometimes you also create the competition, because you need to develop the field, right? If you're the only one doing something, then it's also not you're not moving as fast as possible. So I think a competition is always good to have, but we are very, very, in a leadership position concerning the hardware, and also building up the entire software stack, and also having people using it, because in the end, it's really about also the differentiation is in the entire thing. And for us, it's important, and this is also why we set up the roadmap, that we build the ecosystem, and that we are leaders in the hardware, and also develop the software stack, the open Qiskit software stack, and the applications, because for the consumer in the end, it's important that you have a value of it, right? And so we have I think, very, very good technical path in order to keep leadership. We're very confident, and of course, we also have a lot of passion and energy to drive these things forward.
Sure, Dr. Riel. Now, I want to understand what happened behind the scenes when you launched Germany's first quantum computer, which is also being termed as Europe's most powerful, and you had Angela Merkel herself at the inauguration. Tell us a little bit about the days leading to it, and what went through your mind? What were the challenges, and how did you navigate them?
Okay, so of course, the first thing is to build the quantum computer, to create the performance of the quantum computer, to build the system. But for this specific one, a big challenge was actually the pandemic, because we planned everything out. We had the collaboration starting before the pandemic hit the world. And we had also a plan of when the system has to run, when we are building it up, who is, traveling to Germany and working with the local team to set everything up. Also prepare the rooms for the quantum computer, right? I mean, you know that the quantum computer now has moved kind of from the lab to a data center. So we had to also prepare space, the right space in the data center to bring the quantum computer there. And all this, as you can imagine, in the pandemic, is more difficult because bringing in the construction people to prepare the site had some delays. Then suddenly we had the problem that we could not bring people from the US to Germany to help building up the system. These are the ones experienced who have already built up other systems. And so in the end, they couldn't fly, right? They couldn't come because the borders were closed. And of course, we want to keep our schedule and want to deliver in time and also provide the compute in time. And so actually the team, and a really high appreciation to the entire team who made it possible to be in time, but they did actually build up the thing via WebEx. So we had people in the US who had the experience with building up already many computers, and the team in Germany, for them, it was kind of the first time to build the system up there. And they were then guided by the colleagues from the US. And actually, of course, you can imagine it was a completely new experience for everyone. But it all went very, very well. And the team accomplished, they made it run, they made it really very nicely run, and deliver this thing in time, that the quantum computer and the highest performing commercial quantum computer is now sitting in Germany. And we collaborate with Fraunhofer, who actually has a lot of industrial partners to move quantum computing forward and also bring it to applications, which actually guides back to your first question, or to one of your questions. This brings new innovation capabilities, because now there are many different partners. They are in different industries, different domains. They are identifying what is for my industry important, right? Where are my pain points? Where do I need this additional compute power, or where can I make use of quantum computer to innovate and do something different, which I could not do with classical computers? And this type of thinking now, having in Germany with Fraunhofer as a partner to work closely together with the different industrial domains where they come in with their domain expertise, and us and Fraunhofer with the compute and the quantum computer expertise and the algorithm expertise, that's really where innovation is to be created now. And I think, to close your point, this is, I think, also the excitement Angela Merkel has, and also, showed it in the inauguration. And for me personally, sitting there and and being also part of the inauguration, it was like a very impressive moment to be part of, because it's really, I think it's really the starting point. It's really the start of a new era.
And we look forward to the innovations coming out of Germany for this one. Thank you, Dr. Riel. Thank you for taking time out for the interview. And we hope to see more of IBM's research in quantum, and we'll stay in touch. Thank you.
Thank you very much. I appreciate it.